You may have heard that Python is an interpreted language, but what does that mean? How do we go from source code to something that can be executed by your computer? The answer is CPython, which is a program written in C that takes the Python source code and transforms it into an executable. Today, we'll go over at a very high level the steps CPython goes through to do this, and at the end, we'll go through some of the CPython source code to show what exactly happens when you run Python code. The process starts with a Lexer, or tokenizer, which reads each character from the source code one by one and turns them into tokens, which consists of the actual text and the type that the Lexer has identified. For example, the Lexer will go through the first 3 characters and determine that def is a keyword token. This process occurs throughout the entire file, character by character, until there are no more characters. At the end, we have a sequence of tokens and their types, for example keywords like def and return, identifiers like variable names, operators like the asterisk, and literals like numbers and strings. These tokens are then used to create an abstract syntax tree, or AST. An AST is a tree structure that represents the relationships between different parts of your code. ASTs in Python have a root node of module, then the tokens are used to build the tree structure. Each Python construct, like functions, classes, and loops, become a different type of node in the tree. For example, function definitions become function def nodes, while mathematical operations become binop nodes. Each node can have children that represents the components within that construct, like a function's arguments and body, or an operation's left and right operands. The result is a tree that captures the complete structure of the program in a way that can be easily processed by the compiler. CPython then traverses the AST, evaluates each node, and generates instructions known as bytecode, which consists of opcodes and their operands. Each type of AST node maps to one or more bytecode instructions. Some nodes generate simple instructions, while others, like function definitions, generate multiple instructions to handle their complexity. For example, function definitions require instructions to create the function object and store it for later use. Mathematical operations typically generate instructions to load values and perform the operation. Each bytecode instruction is designed to be simple and perform a specific task, like loading a value, performing a calculation, or storing a result. In this example, the first 3 instructions are related to function creation, and the remaining 4 instructions are related to the function body. For the next step, we'll focus on the function body, which is running the code through the interpreter. Like every other step in this process, the interpreter is just some C code that loops through each instruction and executes it. The interpreter uses a stack, which is a data structure where elements are pushed onto the top and popped off from the top. This data structure is last in, first out, meaning the last element pushed onto the stack is the first one to be removed. As each instruction is executed, load instructions push values onto the stack, operation instructions pop their operands from the stack, perform their operation, and push the result back. This continues until all instructions are executed, with the final result typically being popped off the stack and returned. Now let's take a look at each of these steps with some actual code. This code demonstrates how Python's tokenizer works by using the built-in tokenize module. We'll use this module to parse our Python source code into tokens. The showTokens function takes a string of Python code as input, tokenize.generateTokens to create a token stream. And for each token, we'll print its type, like name, number, or operation, actual string content, and the position, which represents the line and the column number. Looking at key parts of the output, we can see that def is a name token that starts at the second line at character 0, or 2-0, and ends on the second line at character 3, or 2-3. Calculate is a name token that starts at 2-4. Operators like the asterisk for multiplications are op tokens, and the constant 2 is a number token. Now we'll look at how ASTs work with the AST library. The parse function will take in the source code and build an AST, and we'll use ast.dump to display the tree. The output shows the complete AST structure. Module is the root node, which has 2 children, function def and expression. Function def has a name of calculate, which in turn has 2 child nodes, args and body. Args represents the arguments of the function, and body represents the body of the function, which is a binop node that has a left value of x, right value of 2, and op value of mult. The other child of module is expression, which represents the call to the function itself, which takes in a constant value of 5. We can also visualize the tree with the graph function of the visualize library. The left side of the tree after the module root node is for the function definition, and the right side is for calling the function. Finally, we'll go through compiling the AST into Python bytecode and displaying it using the dis module. The output shows 2 sections of bytecode, the module level code and the function code. Let's focus on the bottom section for now, which is associated with the function's instructions. We can see there's instructions for loading the variable x with load fast, then loading the constant value 2 with load const, then finally executing a binary op with an asterisk for multiplication and returning the value. Now let's take a look at the CPython source code itself. I'll include a link to the GitHub repo for this, but this code is the implementation of the Python programming language. This is the code that takes in your Python source code and executes it. This is what it means when we say Python is an interpreted language. You write the source code and it's interpreted with a program written in C instead of being compiled down to ones and zeros. This codebase is massive and old. If you look at the top of the file, you can see it was initially committed 34 years ago by the creator of Python. We obviously don't have time to go through everything, and I'll be skipping over some details, but we'll quickly go over how the interpreter executes bytecode instructions. This happens in the C eval file, specifically in the pyeval eval frame default function. This is a massive function that sets up the environment for executing bytecode instructions and then executes them. Again, we don't have time for everything, but as you can see, there's things like opcode predictions, which tries to predict pairs of common instructions to optimize the interpreter, and some macros that make common stack operations more convenient to call. The main execution loop is all the way down on line 1365, and as you can see on line 1366, this is literally just an infinite loop. The function does some more setup, and then finally we get to line 1466, which is a switch statement on opcode. On line 1476, we have the first instruction for our function, which is load fast and loads in a variable. If we click on the opcode name, we can see that all the opcodes for the Python language are stored in the opcode.h file, and each have a number associated with them. All of these opcodes are handled by this infinite loop. On line 1477, there is a call to getLocal, which loads in a value at the memory location and stores it in the value variable. Then on line 1485, there's a macro call to push, which in turn calls basic push on line 1140, which adds the value to the top of the stack. The next instruction is load const, which gets the value from the operand and pushes the value onto the stack on line 1493. Again, I'm skipping over some details here, but I'm just trying to give a general overview of what's happening. The next instruction is binary multiply, which is on line 1618. The first two lines of this case pops two values off the top of the stack. Then on line 1621, we call number multiply, which takes in the values we popped off. And this is actually how Python handles multiplication. It does some error checking and other things, and then eventually calls binary op1 with the two numbers. Finally, after we get the result and save it into the res variable, on line 1624, we set the value to the top of the stack. This value is then returned with the return value instruction. Thanks for watching. Let me know if you have any questions, and consider following me on these other platforms if you learned something.